Okay, this is the review of the Unit 1 Atomic Structure and Properties practice problems. On the AP exam, you will not be allowed to use a calculator, but just for ease of use, there are a few of these math problems that do allow you to use a calculator. So you can see that that's in parentheses. So number 1, you're given, if you read through the information, the key here is 1,300 grams of titanium. And then the question, and it's a good idea to circle that just so you can focus on what you're trying to end up with, is moles. So we're doing starting with a mass and changing it all the way to moles. So when you do this calculation, you've got your 1,300 grams. You need your periodic table. The molar mass of titanium is 47.87. So that gives us 2 moles, and as you can see in your calculator, you're going to have many digits, 27.156 moles. Be careful. There are 2 answers that look good. Okay, so what's the best answer? Because that's always going to be the directions. So hopefully you would pick D. Significant figures of 2 cause us to round to 27. Okay, number 2 is a question. It's about ibuprofen, and is asking about the percent by mass of carbon. So we have this formula for the compound, and it only wants the percent of carbon in the compound. Okay, so when we only need to know about a part of a whole compound, we need to know molar masses. So if I take the molar mass of carbon that is in the compound, notice it's not 12.01. I've got to say 13 times 12.01. Okay, so the total mass of carbon in the compound is 156.13. Try to multiply. So that's the mass of the part, dividing by the mass of the whole compound. And again, you're going to have to take the mass of carbon, add the total mass of 18 hydrogens and 2 oxygens for a grand total of, it looks like it's going to be 206.31 times 100 to make it a percent. So when we do that math, again, you can see you would need to use a calculator. If this was an AP test question, the numbers would be very simple that you could do with a simple in your head or very simply. So when we do this math, we do get A. And really, if you look at this, just the setup of this problem, since carbon has such a large portion of the total mass, based on these answers, really A is the only answer, even without doing the math, that would make sense. Okay, because think about it, to get B or D, the mass of carbon would have to be, obviously it's less than 50% of the total mass. So we can see that A is the only reasonable answer. Okay, I'm going to move down and look at the next few questions. Number 3, lithium compounds are useful in creating electronics such as rechargeable batteries. A lithium compound is analyzed and found to be 18.7% lithium, 16.3% carbon, and the remainder is oxygen. What is the empirical formula of the compound? In your notes, it was handy to use, maybe this would be helpful for you, is to use the little rhyme. So it's percent to mass, mass to mole, divide by smallest, make it whole. So percent to mass, really all we need to do is assume we have 100 grams, so 18.7% of 100 grams is going to be 18.7 grams of lithium. I do need my periodic table so I can look at the molar mass of lithium. So when I look that up, it is going to be, 6.94. So I do that math for lithium, and I get 2.69 moles. Then the next, I need to have another percent I need to change, so I've got 16.3 grams of carbon. Again, you can see you're going to want to use a calculator, so I've got 1 mole divided by carbon's molar mass is 12.01. When I do that math, I end up with 1.6 moles. So you have lithium and carbon. And then the last percent, we're not actually given. It says the remainder is oxygen. Well, we have to think, well, we should be able to determine that number. So if we think about it, if we add 18.7% and 16.3% together, subtract that total from 100, the remaining percent, as it mentioned, has to be the oxygen. So when you do that subtraction, you're going to get 65.5%. So I'm just going to change that to grams. The molar mass of oxygen is 16. And so when I do that math, I get 4.09 moles. Okay, so these are not my subscripts. These are just the mole amounts of these different elements. So remember, the next step is divide by the smallest. So you can see carbon is 1.36. So the carbon, when I divide 1.36 by itself, we're looking for one of these that has a 1, so we know it could still be any answer. I'll divide 1.36 into 2.69, and I can tell, get rid of that so I can see it better. I can tell that that's going to go in twice, so I'm looking for Li2, and actually that narrows it down, but let's make sure 1.36 into 4.09 does go in 3 times, so that confirms the answer is A. Okay, number 4, a 36.04 gram sample of water is boiled. When the steam expands to fill the vessel, how many atoms of hydrogen would be found in the sample? And it says, don't use a calculator because we do need to practice doing math problems without a calculator. So when we take our mass of water, anytime we have a mass, it's extremely common that we're going to be changing that to moles. And so we can tell we're going to go to moles like we did in number 1, but now we have another calculation to do. We've got to go to atoms of hydrogen. So let's go ahead and change these grams of water to moles using the molar mass of water. So when I divide, see, I can do that in my head. 36 divided by 18 is 2. So see, I'm well on my way to being able to do this. And then I look and see, okay, well, in 1 mole of water, I have 2 moles of hydrogen. Okay? But it's not asking for moles of hydrogen, it's asking for atoms. So when you hear the word atoms or number of molecules or something like that, hopefully you will think of Avogadro's number. So I'm just going to round it off. Since we don't have a calculator, there's no reason to write 6.022. So I've got 36 divided by 18 is 2. 2 times 2 is 4. 4 times 6 is 24. Times 10 to the 23rd. And I look and see, well, that's kind of an odd way to write scientific notation. I look at my answers. So when my decimal point's there, I would need to move it another place, which would change that to the 24 exponent. So we can see that B makes sense for number 4. Okay, number 5, looks like it says no calculators needed, so this might be another math problem. The sample of a compound contains 3.21 grams of sulfur and 11.4 grams of fluorine. Which of the following represents the empirical formula of the compound? Okay, so this sounds familiar from a problem earlier. The difference here being we don't have percents. So this kind of problem is very common. They don't necessarily give you percents to start with. They might go ahead and just give you the masses. So remember, we've got percent to mass, we don't have to worry about. We do need to do mass to mole. So I need to look up the molar mass of sulfur, and I see that it is, it rounds to 32 exactly, or 32.1 actually. It's 32.06, so I could just go ahead and round it. You see why we don't need a calculator, because they wanted us to be able to easily divide. So it's going to be 0.1 moles of sulfur. And then I look at fluorine and I see, well, I've got 11.4, but that's a little awkward. I've got to divide it by 19. So not as perfect, but not a problem. Okay, so 11 over 19, and this is a time when you probably want to round, because you want to make your life easier. So let's just say this was, I'm going to round down to make that 10, and I round up to make this 20. That would be 0.5 moles. Okay, but I can tell that because I've rounded, that it's not going to be exactly 0.5, right? It's going to be a little bit more than that. Okay, so when I divide by the smallest, of course it's still going to be this. So I know there's one sulfur, which those are the answers. But when I divide 0.1 into this, I know it's not going to be F5. Okay, so it would have to be, this is really going to be like 0.6. So if I go to the next page, I can see the answer is going to be D. Okay, and there it is. So the answer to 5 is D. Okay, on number 6, we have a copper 2 sulfate pentahydrate compound, and that just means that water molecules are attached internally into this ionic structure. So the substance, the compound is heated to remove the water. When this is analyzed, the results say that the percent water is less than is expected. So this is what we need to focus on. Which explanation for the discrepancy is the best? Okay, so let's just go through all the different answers and see, what's wrong with the ones that are not going to be the answers. So looking at A, after all the water is evaporated, some of the copper 2 sulfate spatters out of the crucible, resulting in a greater mass lost. So if you think about it, we're massing this at the beginning before we heat it, and then we're going to heat it, mass it, that which the mass will go down, we'll cool it, obviously cool it, then mass it, then we're going to heat it again. We're trying to achieve constant mass here. So if some of the solid spatters out, the mass that's going to be lost is going to be too great. So the difference between what we started with and what we're ending with is going to be a large amount, which means the percent of water will be too high, so we cannot choose A. Looking at B, the sample is not heated enough to evaporate all of the water. See, the goal here is to keep heating, cooling, remassing until we achieve a constant mass. But if we kind of get in a hurry and we don't make sure that the constant mass is achieved, meaning we haven't heated it long enough, we won't know that all the water's evaporated, and that would cause the answer. So that B is looking definitely like an answer, but let's consider C and D and double check. C, the sample is heated too much and the compound decomposes into a salt and a non-metal oxide. Well, that sounds interesting, but this would be a gas, and that means that if some of the product is like not just water, is leaving the container as a gas, then we're going to lose a whole bunch of mass. So that's kind of like A, again, too much mass. And then D, only half of the original sample is heated. Well, if we know the mass of half of the original sample and we know the mass after it's heated and achieve constant mass, the percent of water is going to be the same. So that's not the best answer. So definitely want to go with B. Looking at 7, what is the average atomic mass of the elements represented above? And remember, when we talk about average atomic mass, these are weighted averages based on the abundance of isotopes. So notice we have 2 different isotopes here. We have one that has a mass of 10, one of 11, and we can tell based on the these percents of 80 versus about 20%, that the mass of 10 isotope is extremely abundant compared to the one that's about 20%, which is a mass of 11. So if the majority of the sample has a mass of 80%, we know that that's going to skew the weighted average towards 10. So if I look at the answers, I can see there's no way it could be A, because that would indicate, because 10.5 is exactly in the middle, that I had 50% of both masses, and there's no way it could be C, because 10.8 would represent that the 11 mass must have the highest percent. So it must be B or D. And if you get down to this, you could set this up as a math problem and say 10 times, 0.80, the mass as a decimal. And I'll just go ahead and set this up. This is the way to do it mathematically. I say 10 times my decimal form times 11 makes plus, and then we need to obviously do order of operations, and I'm going to round this to 20. You could easily do that math, and you would end up with 10.2. Just because of it being 80 and 20, I was able to just see that it's going to be 10.2 just by reasoning out. I mean, if it was 90 and 10%, then I would have picked D as 10.1. But that's just a math setup, or you could have reasoned out the answer. Looking at 8, it is another average atomic mass question. It's about chlorine, and we're given the weighted average, or that's what we would see on the periodic table. It does say that chlorine consists of 2 isotopes of 35 and 37. Which of the following most closely approximates the relative abundance of these isotopes? Okay, well, we can solve this mathematically, or we can just reason it out. So we have a mass of 35 and a mass of 37. If they were 50-50, B caught my eye. If they were 50-50, then the average on the periodic table would be exactly in between, which would be 36. So we can tell B can't work, because as we see, the average is skewed towards 35, so that means 35 mass has the highest percentage. So I can tell that this has a high percentage, and this would have to be a low percentage. So I'm looking, it can't be half and half. It can't be A, because the average would be close to 37. So that leaves us to C or D. And again, I just reasoned this out. Which one of these is most plausible? Because 35.45 rounds to 35.5. So from that, I could tell it couldn't be this high of a percent of 90. It must be 75-25, and that is the correct answer. Looking at 9, we're going to switch to some electron configuration. Which of the following represents the ground state electron configuration for the Mn3+ ion? If needed, you might want to consider writing out the magnesium atoms electron configuration. And its electron configuration, I'm just going to go ahead and write the noble gas. This is for the atom that's not an ion. So the noble gas that comes before manganese is argon. And then starting after argon, it would be 4s2 and then 3d5. Okay, so what this is saying is if it's 3+, 3 electrons have to be taken away. And in the notes, hopefully you remembered that the first 2 electrons removed are going to come from 4s, and then the last one would come from the d. So we're looking for an answer with no 4s and ends 3d4. And as you can see, B, C, and D all include 4s. Therefore, we know A is our answer. Okay, 10. In which of the following groups are the 3 species isoelectronic? So remember, iso means same, and we're looking for same electron configuration. So if you just kind of, anytime you're comparing like groups of things like this, it's best to look at your periodic table. So if I look at sulfide or sulfur, it has its atomic number 16. So when it gains 2 electrons, it ends up with 18 total. So it ends up as the electron configuration of argon. So what I want to know is potassium the same? Potassium has 19 electrons, plus means it lost one, it loses one, it does also become argon. So first, these two both have argon's configuration, and then the last one, calcium, is atomic number 20, so if it's neutral, it has 20 electrons. If it loses 2, it would have 18 like argon. So all three of these have 18 like argon. You could go through and see that scandium and titanium, they have different numbers of electrons to begin with. They'd have to be ions to even be considered. And then if you look at C, oxide and sulfide, they're in the same group, but they have very different numbers of electrons to begin with. And then the same thing with magnesium, calcium ions, all three of those ions with strontium. They all are in the same group. So this is about same electrons. So that's key to know what that vocabulary word means. All right, and number 11, which of the following ions has the same number of electrons as bromide? Well, I need to know how many bromide has. So I say, well, bromine has 35, but because it's negative, we add 1, so it has 36, just like krypton. So if I look at my periodic table, potassium had 19, but the ion lost 1. The ion lost 1, it has 18, so I know K is not the answer. I go to strontium. Strontium had 38. It's plus 2. It lost 2. There's our answer. I'll go ahead and just do this exercise. Iodine has 53. Add 1, 54. So this definitely confirmed that's not the answer. And then chlorine, atomic number 17. Added 1, 18. So the only one that is like bromide is B, the strontium ion. For number 12, it gives us an electron configuration, and this is a key where, this is where we really want to make sure we're reading carefully, and a lot of times this word might be underlined. It says except. So this is another, if you can see, all of these are really isoelectronic questions. They're just asked in very different ways. So if I look at this, the electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6. That is argon. And if you just want to think, that's 18 total electrons. You could add up the superscripts, or you could just look up, argon's atomic number. So if I go to titanium, and titanium has 22, and if it's plus 4, it's losing 4. Titanium actually would have 18. Okay, I go to chromium. Wow, plus 6. Chromium's 20, atomic number 24. It loses 6 electrons. It also would have 18. I go to sulfide. It has 16. It's adding 2 more. It would have 18. So again, this is our exception. So we're looking for D to be the answer. Let's double check. Vanadium, here we go, is 20, atomic number 23. If it lost 3 electrons, it would still have more than 18. So that is definitely the answer. Okay, 13. Which of the following, these are orbital notations or orbital diagrams, represents an atom that is chemically unreactive? Well, for something to be chemically unreactive, we typically think what that really means is it doesn't need to lose or gain electrons, and the group that does this are the noble gases. So really, I'm just looking for an orbital diagram for a noble gas. And if I look through these, 1s2, 2s2, that would not be it. And then I keep going, and then I look at C. C has, it's 2s and 2p full. That would be the noble gas neon. All right, 14, which represents an atom in an excited state? Every time, if you've noticed, you're asked to write electron configurations, it typically says the ground state electron configuration. Ground state meaning lowest energy possible, our normal filling order. So excited means some electron, one or more, have gained energy or in a higher energy orbital than they normally would reside. So in other words, you're looking for something that has electrons in a weird place that's unexpected. So if the first thing we see is A. Notice there's 1 electron, so this should be a hydrogen atom, but you would never just start off sticking it in a 2s orbital. It should normally be ground state 1s, so we can see already that that is the answer. If you look through the rest of them, all the electrons that are assigned are in a normal lower energy orbital. There are no other answers that aren't abiding by and that's called the off-bow principle. All right, 15. The question, again, we've got orbital diagrams, represents an atom that has 4 valence electrons. The key here is, remember, valence are in s and p orbitals. So if you just quickly try to answer this, you might answer it incorrectly, or maybe you think there isn't an answer. So if we look through here, valence is going to be the outermost energy level. So I'm just going to circle all these that are outermost. And then here, really 4s is outermost. So which one of these has 4? Well, we can see it would have to be B, because it has 2 electrons paired in the 2s, and then we've got 2 in the 2p, so that would be a total of 4. Number 16, this represents an atom of a transition metal. We know transition metals have D electrons, so I'm looking through these 3 choices, and then unfortunately D's on the next page, but I can see that there's no way any of these could be the answer, because there are no, the first D orbitals are in the 3rd energy level, and it doesn't even get up that high. So when we go to D, we can see there's no question. That must be the answer. All right, for 17, which electronic configuration represents atoms of the element having the highest second ionization energy? So that's, that's a lot to consider. All right, so remember, the first ionization energy is the energy it would take to remove the first electron from an atom. Okay, so second ionization energy is to remove a second electron after the first one's removed. So if I look at just what elements these are, okay, so, notice these valence. Here are valence, 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 valence. What I'm looking for is, after the first valence is removed, the second valence electron, or the second electron that would be removed, needs to come from a lower energy level, like a completely new level, because that's going to take a lot of energy. So I noticed for A and B, actually, both of those electrons that would be removed would come from the 2p orbitals, and they're not going to have the same second ionization energies, but they're both coming from the same types of orbitals. If I go to C, I notice, well, there's only one valence electron in 3s, so when this electron's removed, the second electron is coming from a whole different energy level that's much closer to the nucleus and much more attractive. So that's going to be my answer, because if I compare to D, when the 2 electrons are removed, they're both coming from the 3s orbital. So C by far would require the most energy. Number 18, the elements in which of the following have most nearly the same atomic radius. All right, well, this is helpful when you know your trends. Remember, we said as we go across the periodic table, size decreases, and as we go down a group, size increases. So when we're looking for most nearly the same atomic radius, because when we go down a group, you end up with a whole new energy level of electrons, we're not looking for a group trend. It's going to have to be elements that are in this the same period. So let's see what we have to work with here. Beryllium, boron, carbon, and nitrogen, those are all in the second period, okay? Just one right after another. So their sizes are getting smaller, but let's just see what the other choices are. B, neon, argon, krypton, xenon, that's a group trend. We're going to have huge differences in their size because each new noble gas there is having a new whole energy level of electrons. And then if we look at C, same thing. That's straight down group 2. It's not going to be that. And then if I look at D, we've got carbon, phosphorus, selenium, iodine. That's kind of like a diagonal. It's not even in the same group, but again, each new period is a whole additional energy of electrons. So there's no question in this of those choices, we would have to pick the atoms that are in the same period. Okay, 19. All of the following statements concerning the characteristics of the halogens are true except. All right, so we just need to read through and find something that doesn't fit for the halogens. All right, so A, the first ionization energies decrease as the atomic numbers of the halogens increase. So what is this saying? The first ionization energies decrease as the atomic numbers of the halogens increase. Well, what kind of trend makes the atomic numbers increase? They're talking about going down the group. Is that true? Does ionization energy decrease? And yes, that is true, so we're not going to pick A. B, fluorine atoms have the smallest radii of all the halogens. Well, that's definitely true. They only have, 2 energy levels of electrons. Every other halogen has a whole energy level more. C, iodine liberates free bromine from a solution of bromide ion. So it's asking, can iodine, which is below bromine on the periodic table, replace it? This is really a single replacement rule. And we know that can't happen. If you're not sure C is the answer or not, go ahead and let's see if D is true or not. Because I feel like I would know that, but many of you may not. Is D true? Fluorine is the most electronegative of halogens. C, if you weren't sure about C, what that meant or what that was referring to, you could confirm you did know D was correct, and so therefore you could just assume, hey, the answer must be C. Looking at 20, we're talking about effective nuclear charge. So again, we think about protons here. The effective nuclear charge experienced by the outermost electron of sodium, okay, so I'm thinking of sodium. Sodium has 11 protons, is different than the effective nuclear charge experienced by the outermost electron of neon. Neon has 10 protons. So we're talking about how the number of protons attracts the outermost electrons, which we call valence. The difference best accounts for which of the following? A, something about melting point. No, it couldn't be melting point. Fewer naturally occurring isotopes. Well, effective nuclear charge really has nothing to do with isotopes. That's about different masses and things. C, density. Greater density at standard conditions. I think they're just throwing in some of these things to see if you even know what this is about. And then D, sodium has a lower first ionization energy than neon. Well, effective nuclear charge does contribute to ionization energy, and the reason, even though sodium has one more proton than neon, that one proton is located in the 3s1 orbital, and neon's electron there, 3s1 electron that's where sodium's valence electron is located. For neon, it's the first valence electron that would be moved would be coming from 2p6, so we can see it's going to take less energy to remove that, and we know that ionization energy is a periodic trend we've been discussing. Number 21. The first ionization energy of magnesium is 738. A good estimate for the second ionization energy of magnesium is, okay, so we're saying 738 is to remove magnesium's first valence electron. But if we need to actually think about, if I look at magnesium, this is its electron configuration. Okay, so it's going to take 738 to remove one of these, and then to remove the second electron. Notice it's still a valence electron, so it's not going to have this huge increase unless it was coming from a lower energy level. So we would expect, if it's this one 738, it can't be less, so it can't be A or B, it must be C, because it's going to take a little bit more energy to remove the 3s1 electron, because you have now magnesium as a +1 charge, and you've minimized repulsions than what you've had before. Okay, 22. Which of the following is the reason that the ionization energy generally increases from left to right across the first period? Okay, so from left to right. Okay, so we're saying that it increases. So again, I'm very visual. It helps if you're writing this down, and it's asking why is ionization energy increases. So when we answer this question, if you can, this is an example where you might want to go ahead and think about what's the reason that's happening, and then you're kind of looking for the correct answer, because sometimes when you're reading a bunch of different sentences, it can be confusing. So A says, as the atomic number increases, the electrons are harder to remove. That's true, but is that a reason? Like, what is it about atomic number? So that's a little vague. B, ionization increases as atomic number increases in a period. Well, that's also true, but is asking is the reason. So A and B are really not specific enough. It must be C or D. As the atomic number increases, more electrons are added to the atoms, thus increasing electron-electron repulsions. Okay, we know electron-electron repulsions are a real thing, but electron-electron repulsions cause size to be larger. So it can't be that, because we know the size is decreasing, which is causing the ionization energy to increase. So let's look at D. As the atomic number increases, more protons in the nucleus cause an increase in the effective nuclear charge, and that is the reason. So hopefully you could think of that reason and then choose the right answer. All right. What is the best explanation for the decrease in first ionization energy moving from beryllium to boron? Okay, so beryllium to boron. So notice, again, every time we're comparing two elements, I always go straight to my periodic table. Beryllium's electron configuration ends 2s2. Boron is right next door, but it's 2s2, 2p1. So that's the difference here. So what's causing, because we would expect, as we're going from beryllium to boron, we would expect an increase. So this is like a discrepant event. This is unexpected. So let's see which one of these explains this correctly. Moving from beryllium to boron, more electrons are added to the atoms, thus increasing the repulsions. Okay, that's true, but they have different numbers of protons, and it's really where these are located. So that. Don't get tricked into picking A, because that really is not a good explanation. B, moving from beryllium to boron, more protons in the nucleus attract the valence electrons, making it harder to remove the electrons. That's true generally, but here it's not, because boron has one more proton, yet we're saying it takes less energy to remove this electron. So that's the normal reason it's not applying in this special circumstance. C, the electrons in beryllium are being removed from a full subshell, which is more stable than a half-filled subshell in B. Some textbooks actually mention stability based on filled and half-filled shells. That is not a reason. That's an observation. Okay, D must be the answer. The electrons in beryllium are located in the 2s subshell, which is closer to the nucleus and thus harder to remove than the 2p electrons in boron, and that is correct. We have this unexpected dip in ionization energy because the 2p electron is slightly more distant from the nucleus, therefore less attracted, and is taking a little bit less energy to remove. All right, 24. The table below shows the first ionization energies of an element X in kilojoules per mole. If Y is a halogen, which compound will it make with element X? All right, so I've got to figure out from these ionization energies what's the charge of element X. Okay, knowing Y is a halogen tells me that Y has a -1 charge. So you can see, that's how we write formulas, as balancing charges. So let's look at our ionization energy. 738, 1450, and then this huge jump. So this is where you're supposed to realize to draw a line. This is the dividing line between valence electrons and core electrons. So if there are two valence electrons, those are the two that would be removed. So that means that X is a +2 ion. We know Y is a halogen, so it's -1. What kind of compound would these form? Well, it would have to be 1X for 2 Ys. So B. 25. the reactivity of alkali metals increases going down the group, which is the correct explanation for this trend. Okay, so alkali metals, they're talking about group 1. You might want to look at group 1. That might help you. As we know, going down the group, you could even think of your trends. The size is getting bigger going down the group. Ionization energy is increasing. Ionization energy is going down. All right, so let's look at our choices. A, the ionization energy decreases as you move down the group, thus it requires less energy to remove the valence electron and results in greater reactivity. That sounds great. Let's make sure and consider all answers. B, the greater nuclear charge as you move down the group results in a greater ability to attract electrons to the atom, thus making them more reactive. There are more protons, but there are more energy levels of electrons, so they're kind of mixing two things together that aren't the reason. C, as you move down the group, the nucleus's stability decreases, thus causing an increase in the number of radioactive isotopes, hence an increase in the reactivity. We don't actually study nuclear chemistry in AP Chem, so we know it's not going to be about radioactivity. D, the greater mass as you move down the group causes an increase in kinetic energy for any given molecule's velocity. The increase in kinetic energy accounts for this increase in reactivity. Well, when we study gases, and maybe you remember this from last year, the greater the mass, the lower the velocity. Okay, so the only one that really works is A. All right, moving to the next page, 26. Nitrogen's electronegativity value is between those of phosphorus and oxygen. So again, it's a good idea. Let's see where those are. So oxygen is to the right of nitrogen. Phosphorus is right below it. So it looks like this on the periodic table. N, O, P, and then F is right there, which we know is the highest. Which of the following correctly describes the relationship between the three values? Okay, so the reason for nitrogens is not as electronegative as oxygen, but more electronegative than phosphorus. So A, the value for nitrogen is less than that of phosphorus because nitrogen is larger. So is that the value of nitrogen is less than that of phosphorus, but because nitrogen is larger? See, that what they're saying is incorrect. Okay? Nitrogen is more than that of phosphorus, and nitrogen is smaller. It has one less energy level electron. So be careful. Like, really think about the words, because it's easy to get, not pay attention to less and larger and things like that. All right, B, the value for nitrogen is less than that of phosphorus. Okay, that says that correctly because nitrogen has fewer protons. Okay, fewer protons, but greater than that of oxygen because nitrogen has less valence electrons. Okay, they're mixing up two different things. If it's about protons for one, it's going to be about protons for the other. Or about electrons for one, it's going to be about electrons for the other. They're not hitting all the valid points. Let's keep going. C, the value for nitrogen is greater than that of phosphorus. Okay, that sounds good because nitrogen has less electrons, but less than that of oxygen because nitrogen is smaller. Is nitrogen smaller than oxygen? No, it's not. And then when we look at D, the value of nitrogen is greater than that of phosphorus because nitrogen is smaller. There we go. But less than that of oxygen because nitrogen has a smaller effective nuclear charge. That's it. Those questions to me are hard because you really have to think about every part of the statement to see if anything is false. All right, 27. The first ionization energy for a neutral atom of chlorine is 1.25 megajoules per mole, and the first ionization energy for a neutral atom of argon is 1.52 megajoules per mole. Okay, so right now we've got chlorine and argon. They're right next to each other in the periodic table. How would the first ionization value for a neutral atom of potassium compare to those values? So chlorine and argon are at the end of the third period. Potassium is at the beginning. That's the third period. This is at the beginning of the fourth period. So what this is saying is these energy numbers are to remove the first valence electron from chlorine and argon how would it compare to remove the first valence electron from potassium, which remember is in 4s1. These are in 3p. These both have 3p valence electrons as the end of their electron configuration. So what would we say? Well, hopefully you're kind of getting used to these kind of questions. The higher the energy orbital, like 4s, it's going to take less energy to remove that electron because it is a greater distance and less attracted to the nucleus. So it's got to be C or D. So let's look at those. We know it's not going to be greater. So if we look at C, it would be less than because there are more electrons in potassium, meaning they repel each other more effectively and less energy is needed to remove one. Okay, it's not about, when you're comparing three different things like this, it's not going to be about electron-electron repulsion. So it can't be C. Let's make sure D is correct. It would be less than both because the valence electron of potassium is farther from the nucleus. Yes, there we go. Again, some of these can be tough. You just have to take your time and read through them. All right, 28. Photoelectron spectrum for which of the following atoms would show peaks at exactly 3 different binding energies. Remember, every type of orbital has its own peak. So look at beryllium. That is 1s2 and 2s2, so beryllium would have 2 peaks. Neon is 1s2, 2s2, 2p6. Notice all of these, if that was the 6, would be a peak, so that would be 3 peaks. So that's kind of tricky. Let's look at C, sodium, 1s2, 2s2, 2p6, 3s1. So that would have 4 peaks. 1s2, 2s2, 2p6. I'm sorry. Oh, there it is. I didn't see that electron over there because it says aluminum. So it might even help you actually to write out, instead of looking at these pictures, now that it might help you just to write out the electron configuration, because we know that each of these orbitals has its own peak. So you could see for aluminum it would be 1 peak, 2, 3, 4, 5. So if you did that for all these, it might be the easiest way to do it. So we definitely want to pick B. All right, 29. Which element would have a photoelectron spectra in which the peak representing electrons with the lowest ionization energy would be 3 times higher than each of all of its other peaks individually? Okay, let's look at the other 2 answers. Neon and sulfur. So neon and sulfur. Okay, so which element would have a photoelectron spectrum in which the peak representing electrons with the lowest ionization energy? So what peak has lowest ionization energy? It's going to be the last one, the valence. Would be 3 times higher than each of all the other peaks individually. This is where, again, I would highly recommend electron configuration. So 1s2 for carbon, 2s2, 2p2. See, all 3 of those peaks represent 2 electrons. They would all be the same height. That's not the answer. If I look at nitrogen, 1s2, 2s2. This would be 2p3. So that last peak would be a little bit taller, but not 3 times taller. Not nitrogen. Neon, 1s2, 2s2, 2p6. Okay, that looks like our answer because you have these first 2 peaks are the same height, and then that last peak would be 3 times higher. And then let's just check sulfur, 1s2, 2s2, 2p4. This peak would be twice as high, so it's definitely neon. Okay, number 30, which of the following represents the first electron affinity of chlorine? Okay, remember the definition of electron affinity. Affinity is gaining electrons, the opposite of ionization energy. So we need, and it has to be an gaseous atom. So which one of these is a gaseous atom gaining 1 electron? And it is C. If you look at C, it's losing, so that's ionization energy. B is not an atom, it's starting with an ion. D is diatomic, that's breaking a bond. It has to be A. 31. Which of the elements above has the smallest ionic radius for its most commonly found ion? Okay, so we really have to look at these. So we've got O2 minus, LA, you have to find where that is. It has, it's in lanthanum, is in the 6th period. That is going to be large, so we don't even have to worry about that. Rubidium is Rb plus, but when it loses that one electron, it is like krypton. And krypton, I don't want to put brackets around it, krypton has 36 electrons. Okay, so krypton is in the 4th period. So it has electrons in the 4th energy level. Magnesium is Mg2 plus. When it loses 2 electrons, it has 10, and it is, like neon, right? And then if I look at oxide, I didn't do that one. It had 8. It also has 10. So it's really the smallest is between A and D. So which one of those is smaller? They both have the same number of electrons. It's saying which one has the smallest ionic radius. Well, it's going to be the one that has the highest effective nuclear charge. So we can't pick oxygen. We've got to pick D, magnesium. Magnesium has 12 protons in its nucleus attracting those 10 electrons. Oxygen only has 8, or oxide only has 8. Okay, and then the last one here, which of the following best helps to account for the fact that fluoride ion is smaller than the oxide ion? Very similar reason. They're right next door to each other. Oxide has 8 protons and 10 electrons. Fluoride has 9 protons and 10 electrons. So they're isoelectronic, just like this we had in 31 with oxygen and magnesium. So which one's going to have, it was telling us fluoride's smaller, but why? And it's because of protons. Okay, so we're looking for which one has the right reason, and it's B, larger nuclear charge. They just left off the word effective. They're saying the same thing. 33 has some really good online practice if you need some more help with PES.